Hello and welcome to the presentation. Today we'll be demonstrating a little bit about Docker and Kubernetes and starting with a little bit of history of containers and what to do with them. So first, we're going to go over containers, a brief history, where they came from, what their purpose is, and then we're going to continue on to a brief discussion about Docker, the OCI, and the CNCF, followed by container orchestration and a brief history of where that came about, and continuing on to one of the biggest container orchestrators in the market today, Kubernetes. We're going to discuss a little bit about what it is and what it isn't, what it can do and what it should not do. Followed on a little bit is a small discussion regarding microservices and monoliths, and basically should you or shouldn't you? And then a little bit of Q&A at the end. So, in the beginning, in the dark ages, as they say, with Unix, there was a concept called chroot. This is a command that was used to change essentially the root location of the current user. And basically, it was designed to change up a little bit which user context a process was going to run in. And so this was sometimes used to have certain processes running separate from other processes so they wouldn't intermix or interfere with each other. That concept kind of evolved a little bit, and eventually there was a concept called the chroot jail, in which a particular process would be strictly isolated. It literally could not communicate with other processes deliberately by design. So there were, of course, various ways in which that was circumvented. You could, for example, chroot from within a chroot process, and so on and so on. So over the time, that concept kind of evolved and matured. And with the Linux operating system, sort of the natural successor to Unix, there arose the concepts of C groups and namespaces. And so this is a natural evolution, of course, of chroot, and this is further designed to compartmentalize the various processes. So with C groups and namespaces, you have the ability of isolating the network connectivity, the storage, the processes, and various other aspects of a particular application or process. And so you could make it so that the networking of a particular application is unable to access or interfere with the networking of another application. You could, of course, also, within the name, as it implies, group together various applications so that they can communicate within each other and yet still be isolated from other ones outside of that group. So, as that continued to evolve, this concept of virtualization and isolation and sandboxing further evolved. And so, continuing down that road, additional ideas popped up. One such idea was the virtual private server. So you could, for example, within one individual server, describe several different virtual servers. And so you had the ability of running various applications all together simultaneously on one particular server without them interfering with each other. And this was designed to, of course, be more efficient. You had the ability of running multiple processes on one machine. It meant you didn't have to dedicate an entire machine to every single process. Because in many cases, your hardware is quite beefy, especially in an enterprise. You're going to be buying these very beefy servers. And so very frequently, those servers are not utilized to their full potential. So now you have the ability of running multiple processes on a single box. You can actually maximize the ability of a particular server to be utilized in your environment. And so this concept continues to evolve. There are other ways that this is done other than virtual private servers, but one way that this evolved was within VMs. And so you've probably heard of some of the big players in this game, VMware, the Microsoft Hyper-V, even Citrix Zen Server, and others. These are divided into two subcategories. And so the first category that arose was kind of a natural evolution of this virtualization process. This is called the Type 2 hypervisor. Obviously, since it's number 2, you can tell it's a bit of a retronym. But Type 2 hypervisors are designed to run as processes on top of another operating system. So essentially, you're running an OS, sandboxed, virtualized, on top of another OS. And so you can run a Linux operating system on top of a Microsoft operating system, such as with Microsoft Hyper-V, you could run a CentOS server, or you could run a Microsoft operating system on top of a Linux operating system, such as running a Windows server on top of the VMware or Citrix Zen server. And so this is a way of further dividing your existing hardware into smaller servers. You're not forced into running one particular type of server on top of your hardware. You now have the ability of running a Linux server, a Unix server, a Windows server, and maybe other types, all on the same hardware at the same time. In some cases, this is really beneficial because you add further isolation to the resources. You might want one particular server to have its own dedicated hardware. Now, in this case, it's virtualized hardware, but you might want to say, I want this particular server to have this 40 gig hard drive, and I don't want any other servers to have it. You can also further divide your resources by networking. You can have one server have access to particular networks. And this kind of concept continues on and on. Now, as this became very useful in the environment, VMware, honestly, and some of the other vendors exploded almost overnight in regards to this. This became a massive cost saving for many enterprises because they were finding that many of their servers were having very low utilization. So they would have one particular server sit there doing next to nothing. You might, for example, have a mail server, and it's a very important function in your environment, but it's not terribly utilized. Now, with this virtualization concept, they have the ability of running a mail server and maybe a web server or a storage server or various other kinds all running at the same time in this hardware. So your utilization of the server, which maybe with just the mail server is 5% or less, can now rise. You have the ability of running additional servers. You could have 20, 40, or higher percent utilization depending upon your environment. It's estimated with hypervisors that and VMs that the average utilization of a server is around 20%. That sounds pretty low, and so you'll see why this continues on a little bit here. So, following on this concept, we want to be more efficient. We want to use our existing expensive hardware in more and more efficient ways. So the problem with a Type 2 hypervisor, of course, is that you now have a very heavy OS running on top of another very heavy OS. And the more OSs you have running out as a virtual system on top of the other one, the more and more resources are essentially wasted to running the operating system and not utilized for running the applications. So the Type 1 hypervisor is a way of making this thing more efficient. You're now stripping out a lot of the very heavy resources in your hypervisor and reallocating them back to the pool essentially for your virtual machines to be able to use them. So in this particular case, the distinction would be, for example, with VMware Workstation or Fusion, where you're running an application on top of the OS, and now you're changing it up to use VMware ESXi. So ESXi is a much lighter weight operating system compared to Windows, and so you're dedicating a lot less resources to it. So that's one way that these have been made more and more efficient. This continues a little bit further down the rabbit hole, and we end up with containers. So containers are a way of further optimizing this process. So as I mentioned before, OSs are kind of a bit of a bloat. And so you got a little bit of efficiency with a Type 1 hypervisor by removing the bloat of that operating system. But now you still have the bloat of all the guest operating systems. You have to have every single VM with its own operating system. And that, of course, is a waste depending on how many you have. If you have one heavy physical server with a whole bunch of VMs on top of it, because let's say for whatever reason your application doesn't like to exist with itself on one system, so you have to install multiple instances of an operating system to run each instance of that application. One example of this might be, for example, Microsoft Exchange Server. It does not allow itself to run simultaneously on one system. So every single instance of that now has to have its own guest OS, and that is a whole bunch of wasted resources. Every single additional instance is further waste. So with containers, and I'll note my example is a bit poor here because Exchange does not have the ability to run inside of a container, but containers are a way of taking the application and isolating it in the same way that VM would isolate the OS. It now can isolate the application on top of the existing OS. So, as you can see in this graphic here, you no longer have the guest operating system running in this particular case. You don't have to run the hypervisor. Now, typically you wouldn't usually use a Type 2 hypervisor when you had the ability to use a Type 1. But in this particular example, you're showing that they have even more efficiency by taking that away. So you have a host operating system such as Microsoft Server or CentOS or what have you, and you would put on top of that the container framework. So it would be Docker or other tools like that. And because a container has the ability of leveraging the existing host operating system, it only has to add on the additional bins and libraries that host operating system does not provide to the application, and then the application itself. So you get a much smaller footprint per application. In some cases, this can be quite small. The Alpine container, for example, is only about 5 megabytes. We'll talk about that a little bit more in a second here. So you have the ability of running various applications with a very small footprint, which means you can now run many more instances of these on top of a particular set of hardware. Docker, for example, estimates that if you were to run your containers directly on a host OS versus putting them inside of guest operating systems as VMs, you can actually have about a 40% efficiency increase with the exact same workload. So that's a pretty significant savings right there. Then, of course, we continued on the rabbit hole. CoreOS, sometimes called Container Linux, I believe the name changed at some point, and it was bought out by Red Hat in 2017, was originally designed as a way of further optimizing the container host. So in this case, whatever operating system runs the container. So something like Microsoft Windows or CentOS might still have a lot of bloat to it. And so the same way that Type 1 hypervisors strip down all the bloat out of the OS for the virtualization, a container host OS, such as CoreOS, has the ability of stripping away all the bloat from the container host. So now you're left with a very minimal host OS there as well. And so CoreOS also has further optimizations. It's designed to specifically be very easy and manageable within a container framework. So then, of course, we continue. This game plays itself out over and over again. We want to further optimize our stuff. Containers themselves, of course, can be optimized. And so I mentioned earlier, Alpine is a very small container. You can see on the graphic here on the right that this has been going for some time now. That 11,000 megabyte container down there at the bottom, that was Server 2016 core. When they migrated to Server 2019 core, you can see they dropped that down to just 4.7 gigabytes. And then it goes further and further from there. So, for example, about 326 to run the 1903 core runtime, or 320 for the Server 2019, and down from there. The baseline 250, and if you take the .NET application runtimes for Linux, actually, Microsoft now provides those. You have the ability of running .NET Core on top of a Linux operating system. You can go further and further. So there's a Debian, there's an Ubuntu Bionic, and then there's Alpine itself. So you can run a .NET application on top of an OS, essentially, for only 86.5 megabytes. That is incredibly small, especially when you compare it to the Server 2016 Core image. And Core, don't forget, was itself an optimization of the full desktop experience OS. And so this just goes on. There's not much you can do after 5.8 megabytes, but there are always more and different ways to continue down this optimization. So, Docker itself, you can see the little graphic here on the side here. It works on my machine, then we'll ship your machine. And that's how Docker was born. It's a little bit of a joke, but it has some sincerity to it. It's the idea that within a particular environment, a particular application might or might not work depending upon all the variables that are there. So one advantage of a container is it expands upon that original idea of the sandboxing of various processes, but it further takes that and it standardizes things. So you can make sure that you have the exact same bins, libraries, base operating system, applications, everything that's required to run your application, and you smash it all together into a container, and that container then becomes a standardized unit. And so you can run that standardized unit on any hardware, and you'll get the exact same result. Now, there's some caveats to that, because the container OS, of course, has its own place to play in this discussion. Firewall, for example, networking, all kinds of things have the ability to make problems, but you now know that the actual application is running in the exact same way. There are things outside of that application on the container host that have that place to play, but the application itself is running in the same way. You can, of course, spin up that exact same unit multiple times on that container host and have it run the exact same way. So Docker itself arose as an evolution of that old school process of virtualization using namespaces and C groups, but it's not the only containerization service out there. There are other ones. For example, Rocket was one that was developed by another group. Now this graphic here is a little bit misleading. It was not developed by Google. It was developed by another Silicon Valley startup, originally known as Rocket and then shortened to RKT later on. It is a competitor to the Docker framework. It's also not the only one either. There are additional ones. But Rocket and Docker had a bit of a history with each other. They fought each other hard to win market share. And the reason that this is important is because that infighting started to threaten the ecosystem for containers themselves. After time, they realized that this was a problem for each other, and they actually kind of came to a bit of a truce here, and they realized, well, it's important for us to be able to promote containers of themselves, and we don't want our market share war essentially to kill containers out. So we need to be able to work together on this. And so they worked together with the Linux Foundation and came up with a new group called the Open Container Initiative. And the Open Container Initiative was a sub-organization within Linux Foundation designed to promote containers itself. And so they came up with a standard for containers, the way they should work within environments. And they made it possible for folks to choose easily within particular environments to run Rocket or Docker containers without having a significant difficulty in switching back and forth or running them both simultaneously. And that continues on a little bit more with the Cloud Native Computing Foundation. This is a bit of an extension. So the same way that Docker is kind of the underlying framework for Kubernetes, the OCI is the match for containers. CNCF is the match for the orchestration. You can see a bit of here. Docker has a long history of making lots of commitments to the OCI, starting with their framework of libcontainer and going all the way down to the basic OCI runtime format so that it's now standardized. So, Docker has standardized containers, and the way that you standardize the build of this container is through, of course, the declaration file. It's called a Docker file. Here's an example here, and what this image does, as you can see, is it's got a builder and a final build group, and that very first line, from, dictates where it wants to start with a container. Now, this particular one starts with that Microsoft image. It's a .NET image. And so it's going to take that image from the Docker Hub, which of course is the Docker online repository for containers. And one of Docker's core tenets is that any image that's posted to the Docker Hub will be publicly available to everyone who utilizes it. And so that's important to note. If you have particular things that need to be done privately, they need to be done within a private registry. But one advantage of this is that many applications are available up there for free, and if they aren't already, they can be made that way. So now what this is going to do is, of course, grab that image, bring it to the system. You can see it's going to copy in there from the host the my app folder and drop it into the my app folder within the container, and then it's going to execute this .NET command. It's going to do the restore, the build, and the publish. And so, as you guessed from the name, this is building an application with .NET. We continue on. Once that's done, it starts a brand new container, and it's going to take the runtime container. It's going to copy in the information. You see it says from 0, which is that original builder image. It's copying the published directory there, the pubdir, and putting it into the my app in this new container. It's setting an environment variable for ASP.NET Core utils, and it's setting the entry point. And the entry point is essentially the application or process that's going to run when this container starts. So it's using the .NET within this container baseline, and it's going to execute that myapp.dll. The last line, expose 80, is designed to expose port 80 from within the container to the container host, which means that other applications within Docker and the system have the ability of accessing that port. Normally, these ports are protected, so when you have a container running, you're not going to be able to access the ports within the container, because remember, this is all isolated with the C groups and the namespaces. That networking is not available to the container host or the other containers. They're not going to be able to communicate with it unless you expose that port. So this is going to build all this. It's going to create a Docker image for you, and then you're going to be able to run that. And so one note of distinction is between a image and a container. So the image is essentially the template for the container that you've built with this process, and the container, of course, is the one that's actually running. So once you take a image and you run it, it no longer matches that original baseline. It becomes its own life. Now you have the ability of taking a container that has run and turning it back into an image. So for example, you don't have to build a container with a Docker file. You actually have the ability of starting one image, making changes to it, and then saving it into another image. So that continues on. So as a brief example here of how Docker images run, they have their hello world, of course. You're going to just do a docker space run space hello dash world. And this is going to take from the Docker Hub, again, the hello world container and run it, which in this particular case, as you can see, is a very simple one on the left here. It's just saying hello from Docker and a little bit of information. It's going to run this particular process that puts this to screen, and then it terminates. You can see down there we're back to the shell after it runs. Now, this is an important thing because a container is built around running a particular application process. When that application process terminates, the container will terminate. It's not designed to run multiple processes at the same time, really, although that is possible. That's a little bit more of an advanced concept. The basic premise here is you're running one executable or one task within this container, and when it's done, it quits. Now, of course, you have various things that can run as servers, which are essentially infinitely running applications. But in this particular case, we've executed some text and we've terminated. On the right-hand side, this is just a fancier version with a little bit of a graphic. You can see that this is the whale say, cow say, hello world app. It's the same basic principle. So again, just a little bit of a rundown with the way running a container works. You're calling the Docker, and then you're telling it the run command. These slashes just denote a new line here, part of the same command. -D is going to daemonize that process, which means it's going to run it non-interactively in the background. The alternative, of course, is IT, which is the interactive mode, which means you have the ability of interacting with it. So if it's a shell, you have the ability of issuing commands to it and so on. The next line there, -N, is setting the name so that the name of the container is going to be Redis. Now, otherwise, if you don't do this, it's going to generate a random name for you. It's going to have something silly like argumentative Hitler. Yes, they do use very strange, famous public figure names for their containers. The -V command, what this is going to do is it's going to set a Docker volume or a Docker volume map. In this particular case, this is a map. You can see it's marking the C Redis data redis.conf file, and you can do either a folder or you can do a file, and it's going to map it into the container as user local sc redis redis.conf. And you do see this is actually mixing and matching. On the left hand side, the Docker host is a Windows system, and on the right hand side, the container is a Linux system. It has the ability to do that because you can run a Linux container on top of a Windows operating system. A little bit more about that later. -P is the port mapping. You're going to map 6379 in the host to the 6379 in the container. Just for reference, I think of it this way. On the left-hand side is the host, and on the right-hand side is the container. Because on the left-hand side, you're a little closer to the shell. That's just my mnemonic for remembering that. dash dash restart always. This is a restart policy. What this means is that if this container terminates for any reason, the container host has rebooted, or the container host process for Docker or your other container runtime is terminated, when it comes back, it will re-execute this container. There are other options such as unless stopped or never, which means that it would not restart the container if the system came back after a reboot. And then the last line is indicating the container image that you want to use. So in this particular case, we're calling Redis, and if you don't specify the host to pull your container image from, it's going to default to Docker Hub. And then the colon on the right-hand side, this is the tag. So we've got using the 505-Alpine tag, which means that we're going to use version 5.0.5 of Redis, and it is the Alpine image. It's important to note this because most images are built with Debian or some such, but they usually have an option to run as Alpine. Most applications will run successfully, the Linux containers, I mean, in particular, will run successfully with Alpine, but there are, of course, distinguishments between Alpine and Debian and other OSs because the shells are not the same, the amount of libraries and so forth are not available. Obviously, with a 5 megabyte OS, a lot of features have been stripped out to save space. So you may be wondering, if I'm running a container from a public Docker repo, how do I know what's in this image? How do I know that this is safe to run? How do I know what it's going to do when I run it? How can I be certain that it's safe? And a little bit of a respect, you can't. There is a lot of opinion on the matter here that it is better to always build a container from scratch in your own environment. You have the ability to pull source for most of these applications and execute the Docker file yourself so that you know exactly what's going into the container. But you do actually have some tools available to you to determine what's in this container. One tool, for example, is the history tool within Docker. And what this is going to do is it's going to lay out for you all of the commands that have been run to build this particular image file. And so this is a little bit important to note because you're going to see now that every single little command that is run against this thing, so that remember that Docker file, every single one of those commands actually generates a new layer for the image, and every layer is stored independently from each other. So every single new line in that Docker file is actually generated separately and stored separately in a different layer. And so you can see on the left hand side there, it's got an image tag for every single one of these commands. And then it tells you when it was created and who it was done by and how big each of those items are. So you can see that somebody executed a add file followed by setting the command for the container or the worker and so on from the bottom on the way up, and how much space was added per command. So every single image is built out of a bunch of smaller images based on the commands that were used to build that system. Now that's going to be harder to see if you have tried to take a running container and turn it into an image. This history is not going to be available. This is only available with a image built out of a Docker file. So again, you have to be a little bit careful, but you do have the ability of taking these particular images, splitting them out. These are tarballs, and you have the ability of seeing what's in them, so you can look at these files. You can, of course, start these up interactively and do ls commands and other things like that to see what's in them. So another important caveat, attribute of containers is the principle of a stateless application. Containers are essentially built around this framework of cattle versus pets. And so the concept of cattle versus pets is every single application or server or everything that you have is not meant to be treated individually as a special pet. It's if you lose Fifi, you're going to be very sad. But if you lose cow number 1357, it's not as important. You want to be able to make sure that when your applications are running, they don't need to be treated individually with a respect for who they are individually, but as what they do. So you have the ability to terminate a container, initiate a new container, and have it run in exactly the same way with the exact same information, and you want to make sure that that is always the case because it reduces the amount of management overhead. Rather than having to carefully fix a particular individual system when it becomes sick. You shoot it, you just build up a new one, and off you go. This is typically going to be a massive time and cost saving as compared to trying to fix existing systems. So, now that you've got all these containers running in your environment, you've decided to virtualize your web server, you've decided to put in a load balancer with Nginx, you've got maybe a backend that's available, you're starting to run into the headache of how do I individually manage these systems without having to spend all the time individually managing the systems. And so that's where container orchestration comes into play. So Kubernetes is essentially the de facto container orchestrator on the market today. There are other ones available. However, Kubernetes has the lion's share of the market, and it is predicted that the vast majority of the ones are going to just simply disappear over the next couple of years. So these are the features inherent within Kubernetes, and essentially what happens with container orchestration in general. So you have the ability for service discovery, which means that within a particular DNS name, you can reference a application and always have it available via that DNS name, no matter which containers are behind that, and no matter which application is behind that. So you can spin up new applications, new services, and you're going to always be able to reference those based upon those names, which means that one particular container type can reference another container type just by a name without having to know the particular IP address or anything like that. Load balancing, of course, is another important tenet. You want to be able to have the load balance between the various containers of the various types. If you have 10 web servers running your application, you want to be able to spread that load across. And you want to make sure that when those particular applications are available or not available, that the system is aware of that and handles that automatically. So that's where self-healing comes into play. You have the ability to... Now let's back out here. We're going to do replica scaling first. So if you have a couple web servers available and you realize that you don't have enough computing power assigned to your environment, you're being overwhelmed, the system has the ability, you can either manually increase the scaling or you can decrease the scaling if you're not using them appropriately, or you can have the system scale itself. And so that's one of the things that Kubernetes will do for you. If you set it up to do automatic scaling, it has the ability of checking the load upon those containers, and it will increase the number of replicas automatically for you. There are some caveats to be aware of this, so some people try to do this manually instead, but it is the ability to very easily spin up or reduce the amount of processing power that you have for any particular application stack. Self-healing, I was bringing up earlier. You have the ability, if a particular container dies, the system will automatically detect that based upon health checks that you can define yourself or ones that are pre-built in the containers that you're using. And it will detect that, kill that container, start up a new one. If you have, for example, only one container, it will notice that. It'll spin up the new one first, and then it'll kill the old one. It tries to make sure that there's always services available in any particular given service. So they have a cute little button here that says infect service. I'm not sure what that's supposed to mean here, but presumably it's just some kind of malfunction within the application. It detects that as being unhealthy based on the health check that you've defined. So let's say a config file disappears, the application starts giving you 500 errors. It's going to detect that, it's going to terminate that and build you a new one. Killing service, the same way. If you terminate a particular container within a service, it's going to detect that as well. You don't have the necessary numbers of containers running based upon the service definition. Let's say 5, you now have 4. It's going to spin a new one back up for you to make sure that you match that desired state. You also have the ability to do blue-green deployments very easily. This graphic's a little bit misleading here because typically the way you're going to do a deployment in an environment with Kubernetes is you're actually going to start spinning up the new systems first, and then you're going to introduce them to the pool, and so in a particular moment your application is going to be able to access either version. So you do need to be a little bit careful of that, but there are other ways of doing deployments. So you're going to hit version 34 as soon as those containers start becoming available in your load balancer, and then you can set targets for the way that it does the scale out. So for example, you want to make sure that you always have 25% of your containers available regardless of the version. So it'll only kill 25% of your version 33 and start up to version 34. Once that starts evening out, it's going to start doing more and more and more until eventually you reach 100%. This is great, and sometimes deployments are not so great. You need to roll back. It's going to remember those states. You're going to have the ability to do the reverse operation. It's going to have access to that old container. It's going to have access to that old service definition. It's going to be able to do a reverse scale. It's going to go from version 34 back to version 33 if you have some kind of issue, which is really useful because, as we all know, shit happens. So, Kubernetes, as I said, is the de facto standard now, but it has come a long way since things began. And so, in the late 20aughts, Google started this process with a project called Google Borg. And this was their way of automating a lot of these container workloads when this stuff was all still very brand new. And it's not as robust of a feature, or at least at that time, as Kubernetes is now. Because one of the things, for example, that it did not do is it did not have the ability to abstract the networking stacks. So if you ran a particular container on a system, that port then became used. So if you ran port 3000 for that container, port 3000 ran on the host, which meant that the port 3000 was now permanently used. The newer systems now have the ability of doing a lot more abstraction, which means that you can run port 3000 in the container and have it assigned to whatever port you want on the host. You start to spin up number 2, you don't have that conflict. You can run 3000 in the container and 3001 in the host. So that's a magical improvement between these particular things. Now, so, of course, Google being the leader in this, somebody wanted to follow along on this, and they wanted a piece of the action. There goes the story here that I was told, that a Google engineer was at a bar and had a few too many drinks and started to spill the beans a little bit on Google Borg. And apparently a engineer from Apache was listening in, and so they developed their own clone of Google Borg, which became eventually Apache Mesos. So that, as I said, this is another one of the ones that's still available, but it's not as popular. It has fallen by the wayside, but you can still use it, of course. There are other stacks, such as OpenStack, and various other Red Hat and other vendors have their own proprietary versions. Kubernetes came along when Google said, well, you know what? Someone stole our stuff. It's getting very popular. We would like to make this a standard across the internet because we're supposed to be the company that does no evil and does all the great stuff in the world. Plus, we think this would be really cool to sell. So they started making Kubernetes, which is essentially all of the updates over time put together, and built Kubernetes 1.0. Along with the CNCF. The CNCF, of course, being the working group that was assigned to the core container orchestration problem, the same way that OCI was for containers. There are a lot of groups, a lot of enterprises and competitors that are working within the CNCF. So companies that you wouldn't normally associate with being able to work with each other, direct competitors, are all involved in this for everyone's benefit. Red Hat and Solaris, Oracle, all the various companies are all working together on this because it's in their best interests. So Kubernetes has evolved out of the requirements of a lot of different organizations and has active development from those companies. So you're maybe wondering, what's the name Kubernetes? This is Greek for governor, helmsman, captain. It's a bit of a play on Docker. And so Docker originated, this is British slang for a dock worker. You may have guessed it already. It's because they work with containers. So Kubernetes is a Greek term to reference the folks who have the ability of piloting, essentially, the container ships. And then there is a abbreviation for Kubernetes, which is K8S, which seems kind of silly, and you're wondering, well, is it maybe because it kind of sounds like 8 in the middle? Well, it's even sillier than that. It's literally, there are 8 letters between K and S in Kubernetes, and so they shorten 8 letters down to just 8, so you have K8S. So, Kubernetes is a very powerful system. But as all things that are founded in the Linux world, it is a bit of assembly required. It is not straight out of the box functional, and you do need to pick the various parts that you need to run your infrastructure because not one solution fits everyone. So there's a lot of different solutions for a lot of different types of problems. So there's a couple important components. Let's start with the CRI because we've already gone down that road a little bit. CRI is the container runtime. I'm forgetting what the I stands for. The container runtime infrastructure. And so Docker is, of course, a CRI. It is going to be the system that is going to run the container for you. There are lots of other ones. As I mentioned before, there is Rocket, but there is also CRIO, Containerd, and a number of other ones. And so people have been working on this problem again with the optimization for a long time. Folks are trying to make better and more lightweight versions and, of course, win their market share because we like money. But the thing about Kubernetes is that it doesn't really care which one that you're running. It's designed to run within this framework, the CRI framework, which was decided by the CNCF and the OCI as one consolidated method of running any kind of container. And all Kubernetes does is it leverages that API to work within those various products without having any kinds of issues. And this continues down. So we've got the container runtime infrastructure, but we've also got the container networking infrastructure. And so, of course, this is all the various networking solutions because, remember, I mentioned before with Borg, there was the issue of one particular port in a container consuming the port on the host, which could present a problem because some applications don't like having their ports changed. Some applications, of course, you can just run 8080 instead of 80 and things like that, but some of them don't like that. Or in some cases, you don't want that. You want to be able to run a whole bunch of applications without making changes to the container. You want to be able to run it simply differently on the host. So there are different solutions. Essentially, a container within Docker is going to end up with its own networking stack. It's going to have its own internal IP address, which is only visible to itself. And the host is going to do some translation to be able to communicate with it. This goes further with the container orchestration because you now have to deal with the way that containers not only interact with each other on a particular host, but also on different hosts and in completely different networks in some cases. And so you can do various things like encapsulation, overlay, and things like that. So some of the big names in this particular product are going to be Flannel. We've also got Calico projects, which is probably the most popular one within the Linux world. Unfortunately, in order to be able to use this with the Windows Kubernetes, you do have to be a Calico member, Calico Essentials member, which means you have to pay for it. There are, however, other versions. Canal, for example, is a hybrid of Flannel and Calico. It leverages the networking that Flannel uses and the networking policies that Calico gives you. So you have the ability of dictating via policy where particular applications can communicate, which direction they can go, and so forth. We continue on. CSI is the storaging implementation. It has the ability of different ways of accessing storage, NFS, CIFS, iSCSI, and all the various other fun little aspects like that. I've got a graphic down here for etcd. etcd is essentially a database. It is the workhorse for Kubernetes. This is where all of the configuration for Kubernetes gets stored. And so when you have multiple masters within Kubernetes, this is a etcd replica. Each master is going to have its own replica of the etcd information. And so there is a little bit of knowledge that goes into understanding etcd, how to back up etcd, and things like that. So when I say some of them is assembly required, there's actually a lot of assembly required because there's a lot of knowledge that goes into understanding the way Kubernetes works, the way it gets set up, and getting it working correctly. And so we continue on again with that CNI. You can see here the way that the various containers and things are going to interact with each other. We've got the pod, and so this is a concept within Kubernetes, which we'll talk about in a minute here, which is essentially the atomic unit for Kubernetes. Any kind of workload that you're going to run with a pod rather than a container. Now, in most cases, this is going to be a single container. There are a few special scenarios where you're going to have additional containers within a pod. Typically, these are reserved for sidecars. You would normally not do this. So the pod being the atomic unit, you want to be able to have each pod communicate with other pods. And so you have the container integration bridge, which allows a pod to communicate with another pod on the same host. But let's say your other container is not on the same host. Now you have to start working with the container overlay network. This is the CNI I was referencing before, the canal, flannel, whatever. And that has the ability to communicate. And so flannel, for example, has a layer 2 mode, which works very well, which has the ability of communicating with other hosts that are on the same physical network, layer 2, but you may not have all of your hosts on the same network, which means you have to do something else like encapsulation or BGP. Or there's very, very wide range of options available here in configurations. And then again, of course, the VM host network is the backbone of this, which means the container overlay network now has to work as a form of encapsulation within the host network. And it can go worse than that. Let's say, for example, you have some of your infrastructure on Azure, or some of it on AWS, or some of it on GKE. You now need the ability to communicate between those different networks. And so now you have to deal with the infrastructure of that cloud resource. So I mentioned the various ones: Flannel, WeaveNet, Calico. It's a little further demonstration here of the encapsulation that it can do to pass the communication across. This is a pretty in-depth topic, which is a little bit too much for this demonstration here. Kubernetes itself is continuing an evolution of containers. So it is broken up into the various little pieces. So Kubernetes itself will run as containers on your container hosts. You're going to install the Kubernetes installation tool, kubeadm, and you're going to use that to essentially put containers on a particular host designated as the master. And on a master, you're going to have the scheduler, the controller, the etcd, and the API server. Now, Kubernetes is accessed, controlled, managed via a REST API, so there is a REST API server available for you. You can either directly manage this via REST calls, or you can use the kubectl command, which is typically what you're going to do when you're first starting up. And the kubectl, of course, is just a command line REST tool, essentially to send commands to Kubernetes. The scheduler is what's responsible for telling which pods to run on which workers. So by default, of course, it's going to start scheduling the important Kubernetes pods on the master. And there, of course, also is a controller. And so the controller is designed as a way of getting the information from the etcd. And so the etcd stores the information. The controller sets the information, and the scheduler sets the pods. So you're going to have a controller that's responsible for monitoring all the various pods that are running and making sure that they're running in the right places. And if it detects a deficiency or a change that's necessary, it's going to issue that command to the scheduler, and the scheduler is going to be then responsible for changing what pods run in a particular system. The nodes are not going to have all this other stuff. Now, these resources down here at the bottom, the kubelet, kubeproxy, and so forth, these are also running on the master, but they are required for the nodes. Scheduler, controllers, etcd are not going to run on the individual workers. So kubelet is the essentially interface for the Kubernetes master to the individual worker. It's going to tell the worker CRI how to do its job. Essentially, here's the container I want you to run, here's how to run it, and so on like that. It's essentially converting those scheduler commands into Docker commands. Kubeproxy has to deal with the networking, and is going to have the ability to translate all the networking requirements for Kubernetes and the various overlays to the worker. And then, of course, you're going to have the pods for your actual workloads. As I mentioned earlier, the pod is the atomic unit for the Kubernetes. It has the containers running in it, but there are, of course, all the various pieces of information that have to interact with a pod. And so you can, in the pod definition, set a lot of information, and you can set a lot of configuration via the scheduler and the controllers to the pod. So, for example, the horizontal pod auto scaling is one option. You can tell it to automatically schedule additional pods based upon requirements in your environment. If you are getting a certain amount of traffic, if you are seeing a certain amount of CPU load, scale it out horizontally with additional pods, so on and so on. Voluming, of course, you can pass storage as well to the pods, and so forth and so on. Now you're wondering, how do I tell it how to do things? There's a wide variety of languages that can be used, YAML, XML, all kinds of fun stuff. But the basic unit that most people are going to recommend is the deployment YAML. And so you can see here we have a deployment YAML, which defines a Kubernetes resource known as a deployment. And so a deployment is going to be your basic definition within Kubernetes. A deployment is going to give information to the controller to provide information to a scheduler to schedule your pods. So in this case, we're using the extensions v1 beta API to issue a deployment. It's going to have the name of Hello Express. We're going to provide a whole bunch of information in the specifications for this. So you can see here we've got a replica of 1, which means only schedule 1 pod. We're going to give it some information in the template. So of course it's going to use that template for each initial replica. In the metadata, we're going to specify a label, and the application is Hello Express. That's a little important when you work with the other resources. If you want to be able to specify services and things like that, it's going to use this label for that information. If you go to a particular container and you modify the label that's been assigned to that, those controllers are no longer going to detect that, and it's going to, of course, spin up a new one that matches that situation and so on. So within the template, of course, we have additional specifications. We're going to tell it what containers to run within this deployment. So a pod, remember, is the atomic unit, so we can have more than one container in a pod, although we don't normally do this. So in this particular case, we have a container of the name Hello Express. The image that it's running is the Hello Express with the tag latest, and it has an image pull policy. If you don't already have an image available on the container runtime, go ahead and pull it. If you already have it, use that. We can dedicate specific amounts of resources to this container. This sets essentially upper limits. So this particular container can only use 100 megahertz. It can only use 100 megabytes of memory. And then finally, we're dictating the ports for the container. It is going to run this on port 8081. So deployment is the basic resource here that is going to schedule pods. And then we talked earlier about service discovery. We can also define a service. And so a service essentially ends up being a front end for the deployments. This is the way that you're going to access the resources within Kubernetes. So we can have a couple different types. And one of them, for example, is a node port. What this means is that we are going to dedicate a particular port on all of the hosts that is available for accessing this particular service. So in this particular case, we're saying the node port is 30,002, and so the default for Kubernetes, by the way, is 30,000 up to, I think it's 32,767 for whatever reason. That's where it's going to set these. So if you don't tell it which port in particular, it's going to pick a random one in that range. And so that means if you hit any one of your Kubernetes workers on this particular port, you're going to get access to this application. And it's going to do a port of 80 to a target port of 80, which means that it is going to take that and allow port 80 within the container to be accessible via this service. So it's port 80 of the service, port 80 of the container, and port 30,002 of the node, which is the worker. Here's a small demonstration here of a config map, which is another custom resource. And so config maps are very important because we have the ability of dedicating a particular type of configuration and setting it to a particular set of pods or services. And so within this configuration, we can use all kinds of things. If you have environment variables that your application needs to run, if you have a particular config.xml file that you need to pass to your application, you can pass this config map to the pod, and you can have all the necessary information for your application to run through this. And so you can very easily update all of the configurations for all of your particular types of applications just by updating the config map. You no longer have to pass through files or other various things to each individual container, but you just update this config map and restart the resources as necessary. What this means then is you can also have multiple kinds. So you can see here we've got a dev, a test, and a prod config map. And so you can have, of course, very minor changes within these, which are going to allow you to run that resource. And so you want to make sure that your pods, your containers, are atomic. They have the ability of running in any of your environments. And the only difference is going to be the config. It's going to say, okay, when I start, I'm going to access this database, and I'm going to serve myself in this port at this name, and so on and so on. And that's defined all in the config maps. So you don't need to make changes to the pod to run in different environments. You make changes to the config map. Secrets follows on to that. It's a special kind of config map, and it's designed to pass in, as it sounds like, secrets such as private keys for SSL certificates, passwords, and things like that. And this functions in a special way. It is a little bit environment specific. With Linux containers, for example, it has the ability of passing in an encrypted volume to the container. The container has the ability then to read that information and load it up. So it has the ability to read essentially a file from disk. You can also pass it in as environment variables. One thing you need to be careful of that, though, is, of course, any application that runs within the container has the ability of accessing that environment variable. So if the container is compromised in any way, it will have the ability to read that. On the Windows side, the encrypted volumes are not possible, so it's a standard volume, which means, of course, that it's its own security risk as well. So now I talked earlier about services and the ability of accessing these kinds of things. That can get very complicated if you're dynamically assigning node ports all over the place. You don't also want to have your users accessing port 30,002 because if it's a web server, that's very silly. You want to be able to go to HTTPS, domain.com/web and have it go to the right place. You don't want to have to append that 30,002. So there is a concept within Kubernetes called a ingress, and there's a matching ingress controller. So an ingress is designed to be a way for you to do layer 4 and layer 7 mapping within Kubernetes, layer 7 being the more common type. So if you have a web server, you want to be able to have it pass the information through seamlessly. So you can, within your ingress definition, tell it if you hit the Kubernetes cluster and you say you're going to domain.com/web, you can have that automatically pass through to your particular web server, right? You can have your API domain go to your API server, and you can have your back office domain go to your back office servers. And so this is a form of automatic and dynamic routing. You can set up automatic discovery for this as well. And as you can see here, traffic is one of the popular ones, and it will do all kinds of fun things like automatically leverage Let's Encrypt for SSL. That's a little bit more difficult if you're running it, of course, in a non-internet environment. There is, of course, also competitors. HA Proxy has now recently released a ingress controller as well, which is a very powerful web balancer as well. So this is important because you now have the ability to pass all of your connections through one set of accesses and have it automatically pass those through to the right thing based upon your service discovery. So you can have API domain.com, domain.com, backoffice.domain.com, all your other resources point to a single set of IPs. Typically, you're probably going to still be using an external load balancer, so it kind of gets double load balanced, but you now have it to automatically, within the definition within Kubernetes, route the traffic to the particular set of services, containers that it needs to go to. This is very useful because it now means you can change that information based upon a commit for a config file. You can use your continuous integration, continuous delivery tools to automatically change that based upon a commit. So a developer now has the ability to redirect traffic without having to involve an operations team, for example. So as you can see here, this is kind of a demonstration with a cloud. They are recommending that you use app-example.com to hit your Google Cloud load balancer. Of course, if you're bare metal, you can use another product such as a proxy, Kemp, whatever. And that's going to pass that through to the node ports that are available for your Nginx ingress controller. So of course, you're still going to use a node port to have your traffic hit your Nginx ingress controller because there still has to be a way for that to pass through. But then you can see the ingress resource is going to define where the various resources are going to go. And so app-example.com is told to go to the service called app. If it fails to meet any other definitions, it has the ability of falling back to that default backend. So this continues down the line of infrastructure as code. You want your developers to be able to control your environment with involving operations as little as possible. This is kind of that continuation further of the cattle versus pets mentality. You also want to be able to have these resources spawn and die without having to involve individual servers being configured, passed up. They're all going to be automatically configured based upon these declarative definitions. So this is a very easy way for you to be able to spin up additional resources within your cluster without having to spend up the time to spin up those resources. You're going to be using your tools to automatically set up those various resources. If additional capacity is needed within data center, what you do is you have your operations team spin up additional nodes for your Kubernetes cluster, but the actual applications themselves fall within that existing cluster without any interface from your developers. So all of this power within Kubernetes, we can now declare configurations for your test, your dev, your production environment. You can pass through configurations automatically. You can scale up, you can scale down, you can change your versions, you have self-healing, you have all these wonderful tools within Kubernetes. But it's important to remember that Kubernetes is not magic. So one thing, for example, is that folks sometimes forget that it does not have the ability of producing additional resources. It's designed to be a way to more efficiently use your existing resources. So if you have 40 CPUs available in your Kubernetes cluster, that's all you're ever going to have, unless you add more physically. It's not going to magically provide you with additional capacity in your data center. You're not going to be able to run more workloads at the same time if they don't have the resources to do so. Kubernetes is also not easy. This is a very powerful tool, and like all very powerful tools, it is very complex. It is very difficult to run, very difficult to manage, very difficult to set up in the first place, which also means that it is not a set and forget tool. It has the ability to fall by the wayside. If that etcd database gets corrupted or for whatever reason, you now have to recover that, which means you might have to rebuild your cluster entirely. Kubernetes is also a very rapidly developing tool. They have a development life cycle of about 6 weeks, which means that you are seeing new versions all the time, and it is rapidly developing with new features, which is a wonderful thing to do, but it also means that you must now keep up with that. You have to keep your Kubernetes cluster up to date to leverage all those features, and of course, you're going to have security issues as well with that, which means that you need to continuously be managing this. So it is definitely not a set and forget tool. It's also not the only option. It is the industry leader at the moment for container orchestration, but it is not the only way to do it. There are other tools, Apache Mesos, Red Hat OpenShift. There's a lot of other tools available. You don't actually have to use a heavyweight orchestration tool either. You have the ability of managing containers in very manual ways. If you're a small environment that only has a couple containers that rarely ever see any kind of changes or needs for change, you could very easily run a couple containers, say Docker run with a restart always policy, and just make sure they're always running. If you're not doing a whole lot of deployments, that's not a big deal. Maybe your CI tool has the capability of just updating the containers as need be, and that's sufficient for your environment. You could also use other kinds of tools. There are a couple other tools by a company called HashiCorp, which are very useful in this environment. Consul, for example, is a tool which allows you to determine the state of a particular system. And Nomad as a tool is designed to set a configuration on that system. So you could detect a particular state with Consul and set the state with Nomad, meaning that you have the ability to say, oh, I am using too much CPU on this node. I should stop running the container here and start running the container over here. Just keeping in mind, unless you're using a container orchestrator like Kubernetes, it's not going to be able to shift those loads automatically. It's going to have, it's just going to keep running essentially until you to do otherwise. So you need to use these kinds of tools to shift the loads or restart containers. If they die, bring them back, change versions and things like that. But you have these other tools which are much more lightweight to be able to set some of these states. Now, of course, every single tool that you use in an environment may provide some benefit, but it is, of course, going to come with its own cost. Every single additional tool that you have is going to involve somebody learning that tool, setting that tool, managing that tool, making sure it stays up to date, making sure it's not vulnerable, and so on and so on. Kubernetes has this problem. Well, these other tools have this problem. Some of these may be easier than other ones, and so it's important to remember for your particular environment that you take that into consideration. You need to look at all these various resources and think about that. So Kubernetes is also not good for everybody in that same regard. It means that in some cases Kubernetes is just too much. Your environment may not be big enough. It may not be dynamic enough for Kubernetes to be justified. Because like I said, every single tool is going to have its own cost, which means that you need to make sure that you're not following into a trap, which is actually quite popular for Kubernetes. You're now spending more time managing infrastructure than you are managing your actual application. You've now gone in the opposite direction of what you want to do. You want to make sure that you are using these tools to reduce your workload, not increase it. Another option is the Docker Swarm. Within Docker itself, there is a feature called Swarm, which functions in a similar way to Kubernetes. It's a much, much more lightweight version of it, but it has the ability of doing scale ups and scale downs. It has the ability of rolling features and things like that. So it has the ability of doing some of the things that you wouldn't be able to do with Kubernetes in a much more lightweight way. You don't have to deal with the etcd replication and making sure that you have all the right networking and things like that. Some of that's going to be handled by Docker Swarm itself. Some additional tools from this HashiCorp company, and you'll find this company mentioned quite frequently in DevOps. And a very surprising thing that you might find is that these tools are all free. You do not have to pay for any of these tools. And these are very, very powerful tools. So I've already mentioned Console and Nomad. These are basically inventory and state setting tools. But there are other tools such as Terraform, and that is designed in the same way that Console and Nomad can set states for machines. Terraform is designed to build out your infrastructure for essentially cloud. It has the ability within providers to say, on this particular ESXi host, I want to run these particular VMs. Or it has the ability to say, on GKE, I want you to run these containers. Or on DigitalOcean, I want these droplets. It's designed for you to be able to set a desired state for resources within a very large range of environments, which is really useful. Vagrant takes VMs in the same way that Dockerfile takes containers. With a declarative state language, it has the ability of spinning up a VM on a system in the exact same way, so that you have, you don't have that problem of, oh, it works on my machine, it doesn't work on your machine, so on. You can use VMs in the same way. And similar to the fact that you can run containers and applications that way, you could, of course, set Vagrant up to set up your container hosts. So you can kind of have your inception there. You want to make sure your container host is running the same way on every system, as well as your containers running in the same way and your applications running the same way. Packer, of course, is what it sounds like. It has the ability of packing up your applications and all your dependencies in one unique package, doing that automatically for you in a repeatable way. Vault is designed to be a credential manager. It is leveraged within Kubernetes or Docker directly, and it has the ability for various applications to access via a lot of different controls. You can use LDAP and all kinds of different resources, so you can very carefully manage the credentials that your various applications need to use with each other to communicate. Now, as I said before, Kubernetes is not magic, it is not easy, and it is not right for everyone. So in some cases, folks take the microservice concept, which became a buzzword, and they take it too far. In some cases, it really doesn't make sense. As you can see here in this little comic book, it says they came to them with a message, but they could not understand its language. The alien there says, a microservices architecture is only necessary in large, complex dev environment. Most shops would be better off just using simple monolith, following solid principles, and reap benefits from frequent small deployments. And of course, the little natives there say, what? And they're like, screw you. Yeah, it's not always better to run something as a microservice. In some environments, it does make more sense to continue running a monolith. Other environments, it makes more sense to go even further down the road, going past microservices into function-based applications. And so there's a wide variety of tools for that as well. But it's important to make sure that you don't get caught up in the marketing hype and go too far. You're now spending too much time on managing your infrastructure and not enough time doing your deployments and your development. It's very easy to go too far in that direction. And that's it.